record on this computer. There is, you know, there it is very possible for you to pivot into different kind of courses. At Temple, we have an online IS&T program, which basically is designed for people who have a science degree and want to pivot into basically getting a more computer science type degree with a master's. But if you're like interested in computer science and masters, don't be afraid to try to apply, because there's a lot of, especially if you're in biology, there's a lot of coordination that goes on between the two. To the point where when I was at Georgia State, there was this big kerfluffle when it came to hiring a chair for the biology department. The administration wanted somebody. The faculty said, no, we hate that person. So which sometimes happens. And so the chair of the computer science department at the time went and became the chair for the biology department, which he was qualified to do because of his work in bioinformatics and all of his collaboration with biology. It's very easy if you're in computer science to basically, or another degree, to kind of merge those things together, which is part of the reason I like it. Master's in information science and technology. But there's a whole lot you can do. And a lot of what we do in computer science is kind of blended with other aspects, with other things. But there are some things, and I'm segueing right here, which is great. There are some things that are basically clearly under the domain of computer science and a bit of math. And that is what we're going to talk about today, which is cryptography, which is always a fun thing. And I'll talk about what cryptography and cryptanalysis is and the history of it. But before we get started, let me just clear up a couple things. I will be grading quiz 5 by hand. I should have already done quiz 4 by hand. Quiz 6 has been posted. If you had somehow already taken quiz 6 and now there's new questions on that, please let me know so I can reset your quiz. There is one Monte Carlo question and one file reading / dictionary question. It should take you about an hour, but if it takes you longer than that, don't worry about that. But it's just 2 questions. One's on Monte Carlo, one's on file reading, and putting together a dictionary. Okay. No, you don't need to. I'm going to check everybody's questions for quiz 5. You don't need to email me. Yeah. If you schedule an appointment with me or send me an email, I'm pretty much free to meet pretty much every evening. Although I am going to be proctoring some students on some, you know, but like I can meet like up till around 11 o'clock in the evening. That is how late I can go. So if you need to meet with me, but I can show you your quiz after you're done with it. That is the one thing I don't like about the quiz format, that you can't look at it. I will also work on making sure we review on next week for the final exam. And then, again, I'm not giving additional labs for you, any additional homework. Right now, your focus is on the final project. I also want to mention that if you have not turned in a proposal, you need to do so ASAP. You have to turn in a proposal. Yes. Just turn in a link to the proposal. Okay. If that, you know, that's no problem, but it's no problem. But if you turn in a link to that proposal, it also prevents any possible problems that might emerge, if that makes sense, right? It fixes us having to go back and correct something. Okay. So yeah. So let's go ahead and talk about our what we're going to do today. So what we're going to do today is in Runestone. So open up your Runestone book. You'll want to go to scroll scroll all the way down, and we're going to work on something a bit earlier in the book we're going to use some tools that like dictionaries that we didn't necessarily have, that didn't necessarily intend, but that's fine. But we're going to talk about ciphers today, and specifically cryptography. Okay. So basically it's this, again, it's scroll all the way down. It's project 9. I will go ahead and drop it in the chat. So a bit about cryptography. So there's 2 terms that we use for code for when it comes to ciphers in computer science. The first is cryptography. Cryptography is the act of basically making codes and making ciphers and encrypting information so that nobody but the intended recipients can read it. Cryptography is all about basically trying to secure your information, trying to secure messages. The flip side of that is cryptanalysis, which is the art of breaking ciphers. Because if it has meaning, there's always a way to disentangle the meaning, to figure out what the meaning is. So first off, I want to say that there is no perfectly secure system. Okay, if you have not, I recommend anybody who's interested in understanding how, like, quote unquote hacking actually works, to watch this talk at DEF CON, which is entitled "Kill Everyone," Kill Everyone, Steal Everything, and Steal Everything, Kill Everyone, Cause Total Financial Ruin. Which is, it was given in it's a decade old now at this point. It's a fantastic talk, with a very, in-your-face title. And he talks about basically how he's able to basically and what he does is that he's in here, he's talking about how he's hired as basically a security consultant to do some what's called white hat hacking, or penetration testing, which is basically evaluate a company to see what their defenses are and what kind of damage he could potentially do. And they expect, a lot of people expect, like, that what you are going to be experiencing there is like some attack on the network. Encryption is strong, passwords are strong, people are weak. People are very weak points in the system. They have points you can physically attack and threaten. And so he talks about basically, also people are careless. They do things like leave their keys or their IDs around. And he talked about basically, okay, I've got this person's keys. Now here's the consequences of the fact that I've just picked up this person's keys after I got into the building. How did I get into the building? Well, I just was carrying a bunch of stuff with me, random boxes and stuff, and some polite person just held the door open for me because it was just too much for me to carry and open the door at the same time. Or I was just wearing a clipboard and a vest, which is, right? The Marvel Cinematic Universe has it wrong. You don't wear a hoodie, sunglasses, and a baseball hat to go incognito. You wear a bright yellow vest and a clipboard. That's it. You are now, and a hard hat. And now you go anywhere and nobody's going to question what you're doing because you're obviously doing something important. You have a clipboard. And you're obviously not letting anyone nefarious trying to sneak around. Everybody can see you. You're wearing a bright yellow vest. So a lot of damage can be done by non-technical, without a lot of technical know-how, but knowing the technical know-how helps you know what kind of damage can be done by knowing what the weak points of a system are. And again, he's not doing anything illegal. He is literally hired by the companies to do this type of thing, right? But what we're going to talk about is the development of these and history of these strong points. So back in the early centuries, right? There was this giant, state you may have heard of called the Roman Empire. I don't know. It was kind of a big deal at the time, I think. Anyway, now they were in the business of empire building, which means you had generals, and generals need to coordinate with each other by sending orders, right? And coordinating attacks, right? Because you want to make sure that if your troops are going to all attack together at dawn, and you don't want anything to be miscommunicated, right? You want to attack from the south at dawn, and you want the other army to attack from the north at dawn, so that you can flank the enemies and box them in, right? Okay. What you don't want, though, is that you don't want the guy to attack an hour after you're attacking, because then, well, you've just divided your forces, and now they can fight your forces, and then they can turn around and fight the other forces. So you got to coordinate somehow, and coordinating means sending a message. But sending a message means that there's the chance for your message to be intercepted. If you send a messenger, these barbarians, which were literally people, which is literally from the Greek word, meaning basically people who just say bar, 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 right? People who don't speak the real language. So it all sounds like bar. These literal, so these barbarians could capture our messengers, and, literacy at the time wasn't great, but it still existed. So we could read the message. I don't want my messages to be read. I don't want my attack orders to be read. So enter what's called the Caesar cipher, which is the earliest form of what's called a substitution cipher. And the idea here is, with the Caesarian cipher, which is named after Julius Caesar, is that we're going to shift all the letters by 3. The idea here is that if I see a D, it's actually an A. If I see a E, it's actually a B. If I see an F, it's actually a C. So in other words, when I'm writing this down, here they basically did a left rotation. So it's either left or right. But here, what they're doing is basically saying, hey, okay, so it's the other way around for this one. Okay, here, what they're saying is, okay, if I'm trying to write attack at dawn, I'm going to go backwards 3 letters. So anything that's an A is going to become an X. Anything that's a T is going to become a Q, right? 1, 2, 3 letters back. So attack at dawn becomes, so attack at dawn, which is the hello world of the security world, by the way. Attack at dawn is what's used as a test message a lot. Why a shift of 3? Because that's what Caesar wanted to do at the time. But that's a great question, and I'll get into how that is. So right now, so if I do attack at dawn, I'm going to basically get X, and then T's are 3 back, so QQX. And then C would be a Z. And then K would be an H. Right? So we'd get X, QQ, X, ZH, and so on and so forth. And it would just look like to a barbarian who's not in on the joke, like a lot of gibberish. Right? The idea here is that I send X, QQ, X, ZH, and our other general, they know it's a Caesarian cipher. They know that we're shifting everything by 3. So they shift it the other way. Here we shifted it to left. We could easily have shifted it to the right, by the way. Done A as D instead. Or, A as D, and then T as W's, right? And so on and so forth, right? The only thing that you have to do is you've got to make sure that whoever you're communicating with knows how you're going to communicate with them in the first place, right? Now, this is what's called a cipher, okay? And this is different than a code. A code is where we talk in a very visible language, but there's subtext. I'm going to make him an offer he can't refuse, right? That's a code. Okay, so here we're talking about cipher, which is just so that we're going to be academically correct. Now, this is a type of cipher, and one of the most basic type, shift cipher. It's a type of substitution cipher where basically every single letter is replaced by some other letter in the alphabet. We substitute. So in our original message, we are going to substitute every letter with some other letter. Here, it's a substitution cipher with a shift of 3. That's what Caesar cipher is. But there's other ones that exist. And so now we had a huge history. Now this actually worked until basically everybody knew the secret, in which case we needed a new kind of way to do this, because you have only, well, if I know you're using a substitution cipher like this, I only have to try 26 different combinations. Well, 25 really. Another type of cipher is where we basically use something like, basically this became kind of a knowledge arms race. What we had at the time of World War I and the Civil War was the Vignere cipher. And what that is that basically, if we take instead of using every letter having a set shift, everything being 3, instead we're going to use a keyword. Like in this case, it's lemon. So here, attack at dawn, and then we repeat lemon a bunch of times until there's enough lemons for all the characters. And what you do is that basically you do some numerical addition. And rather than making you do addition, they used a table to figure out which letter you needed to, how that encryption worked. But the end result is that attack at dawn with lemon looks like this. But you could still do some frequency analysis on this and figure out if your message is sufficiently long enough, then there's a way to figure it. Also, if you know how the message begins, that also helps, because that gives you a starting point. So this continued until about World War II, where machines basically became necessary for this kind of thing. So this machine handled all the encryption. It's called the Enigma machine. You may be familiar with it if you've seen The Imitation Game. Although I should mention, if you've seen The Imitation Game, Alan Turing was a lot more sociable and less of a acerbic than Benedict Cumberbatch portrayed him as. But that's what you get sometimes when you watch dramas. So anyway, the Enigma machine, the Germans use this to encrypt orders for the movement. And Alan Turing, he worked in Bletchley Park and built what's called the BOM, which is a computer specifically designed to break these messages. Okay, so and the idea here is that this gets into a completely different aspect of computer science, which ties in with psychology, which is all about like information and information leakage. Now that you have cracked the passwords, how can you use this information, this intelligence, in such a way that you don't reveal that you've cracked it, but can still get a tactical advantage? You've got to, well, for one thing, if you are actually going to sync a sub that you know its positions of because of the letters, these are because of the intercepted messages, you can't just sync it for no reason. The Germans aren't stupid. So what you have to do is you have to have you just have to make sure it looks like you're incredibly lucky that you have it, that you've sent out your scouting planes over that position before you sink that ship. Okay, so you've got to make sure that those kind of that basically that a narrative can be created which is more likely than the codes have been broken. So here as our first exercise, and it's not attack at dawn. Here's a secret message. Yes, it's exactly that. It's not letting them know that you know. So here we're gonna work on our first bit of cryptanalysis and try as best you can. So we've got a secret message. Our secret message is called the ciphertext. And when we can read it, it's called the plain text. So the question is, can you decode this message? Okay, now here I'm using a substitution cipher. Okay, now it's not attack at dawn, but there is a hint that your B's are O's. So if you see a B in here, then it's an O in the plain text. So see if you can decrypt the message over here. And if you want, you can, and if you need some more help, there's a matching question over here that can help you figure out to decrypt a few more of the letters on the second activity. Okay, so try to decrypt this by hand, if you can, right? Try to figure out what the hidden message is. So let's take 5 minutes to do that. So a hash algorithm like SHA-1 cipher. A hash algorithm is a cryptographically secure. So SHA is a cryptographically secure hashing algorithm. That's what the SHA stands for. And in that, so what hashing algorithm is that basically it looks at a message. Okay, a hashing algorithm looks at a message or anything, a file, a message, anything, and it spits back what's called a key. And this key is fairly unique. Like very, very, like it's a key, it's like a giant number from a giant range of numbers. But the idea behind SHA is the cryptographically secure part of it comes from the fact that given the output of this secure hash algorithm, you can't figure out what the input was. Now, the useful for this is basically you can send a message and you can send a hash of the message, and that way you can, and basically the hash is a way of saying that you can try hashing the original message yourself, and if this hash does not match the hash I sent you, then it's been tampered with. Sorry, give me 1 second. They can. So the question was, do the pairs work both ways? And the answer is they could. They certainly could. All right, do people need more time? Or do people want me to move on to the answer? Sorry? More time? Okay, right. So now there is no such thing when it comes to breaking codes as cheating, right? Cryptanalysis is all about using what you can get. One of the ways that the Enigma machine was broken by the bum was the fact that they didn't have to go through all the messages. They could use what's called cribs, known messages with known output. So basically, if you had an encrypted message, you don't know how it was encrypted, but you knew what the answer would be, then that's useful information. How in the world would you get that? Well, when you encrypt everything. For instance, say you've got a German basically outposted in the Sahara, basically he's got no action going on in terms of stuff. Then his message is going to be the same thing every day, which is situation normal, nothing to report. If you know what the output of that message is, then you know then you can use that to help break other messages. Similarly, if you know that Germans, that the Nazis, they would sign off their messages using Heil Hitler, almost universally. True fact. So there was no variation to those kind of messages. So very easy to break them. So using any kind of information that's available is good. Now, the information that is available here is the fact that we talked about a bunch of ciphers, but honestly, only one of them is really realistic, which is the Caesar cipher, which is the idea here that we do some kind of rotation. So if B goes to O, then I can just simply copy this over here and try this rotation over here. And if we try this now, we should get C goes to P, L goes to Y, G goes to T, U goes to H. And if we decrypt this message, basically using this key, then we get Python rocks, because the person who wrote this is a bit corny, you know. Okay. Now, the idea here is that now this is a specific this type of substitution cipher, like the Caesarian cipher, which is a shift of 3. This one has a specific name, ROT13, ROT13, which is one of the most simple, which is one of the simplest ciphers out there. It is basically just the alphabet is 26 letters long. So half of that is 13. So if you use ROT13, right, then the idea here is that you can apply the ROT13 algorithm, which is shift everything to the right by 13 to encrypt your message. And then if you apply that algorithm again, you get your output. So basically the encryption algorithm is also the same way as decrypting it for ROT13, which is pretty interesting. So so if you try to encrypt so hello encrypted is URYYB, but if you encrypted URYYB, you'd get hello. So basically the encryption algorithm does its own inverse operation, which is pretty cool. The algorithm provides virtually no cryptographic security and is also a canonical example of a weak encryption because it's so well known. Because also, all you have to do is just kind of check through your different rotations if you know it's a rotation cipher. But it's useful if you want to do something like hide a spoiler, right? You want to post a spoiler onto a social media network, right? You can post it in ROT13, and it's very easy for everybody else to decrypt so everybody else can read the message. But nobody's going to be immediately spoiled by something, right? Yeah. So it's useful in that kind of thing. Everything has a use. Now, so the idea here is, though, that is a bit of an annoying way to do it. Now, typically now back before we had things like computers, typically a way of dealing with the Caesar cipher is that you'd have a little dial like this, that you would rotate the inner dial to line up the letter, so you'd have an easy visual way of seeing what your encryption and decryption were. So you just know, so you know the number as the same number as somebody else, and then you encrypt it like this. You know, it's a nice thing. But here we have something, we have computers to do this for us. So now let's write a program that will encrypt this string, which is stored in plain text. The quick brown fox jumps over the lazy dog, into encrypt it using the Caesar cipher. Okay. So there's a couple ways that we could go about doing this, right? Now, the first way is to like take this thing and manually create a dictionary, basically saying, hey, D of A, D of A is equal to, N, and so on and so forth. And then B is equal to O, which takes a while. But it's useful when we're going to be doing other things, when we do a different type of substitution cipher. For a rotation cipher, though, we can use something a bit easier. We can use math, which is a bit horrifying. And the idea here is that in Python, okay, you got to remember that everything kind of has a numeric value in Python, right? Or every letter is just a bunch of bits. And we can figure out, so we have this command in Python, which I mentioned a while ago, and basically it just languished in memory, which is ORD, because we don't really have a use for it too much, which returns the Unicode point for a 1-character string. A is 97. So in the basically the binary kind of bit representation of A is 97. The bit representation, the numerical representation of B is 98. And you can almost, you know, it's pretty easy to figure out, oh, right. So if it's C, right? So C would be 99, right? No surprises there. And so on and so forth, right? Now, this is again Unicode, but really while we concern ourselves with the first bit of Unicode, which is the ASCII chart, which is basically here's the first 128 characters, things like the bell, the backspace key, hitting the enter key, the slashes, all the symbols, and then basically over here, right? The capital A is 60, has the value 65. This is octal, which is base 8, decimal base 10, hex base 16. And we notice that over here, A is 97, B is 98, C is 99, and all the way up to here where we have 122 for Z, right? So how does this help us? How in the world does this help us? Well, if I did something like this, ord of A plus 3, that gives me 100. Okay, but how does that help you? Well, what I can do is I can throw that, there's an inverse operation for ord, which is CHR. Returns the Unicode string of one character with ordinal. In other words, given a number, tell me what that character that corresponds to. So A plus 3 is 3 letters after A. Makes sense to everybody? Which is D. A, B, C, D, 3 letters afterwards. Okay. And of course, everybody knows that 3 letters before A is, of course, the caret sign. Everybody knows that, the caret sign. Wait a second, that's, hold on, let me check my chart. There isn't a caret in there. That doesn't seem right. I know, I'm just, so there is a bit of an issue here, which is that we have other characters. I have no idea why that went off. Last time, if I just stood in front of it menacingly and walked around. Motion detection, gotta love it. Okay. So, unfortunately, we are, you know, our letters are 0 through, you know, we have 26 different letters, but there's other things besides letters in this chart. So if I did A and subtracted 3 from it, I'd like Z, Y, I'd like to get X back. So how in the world am I going to do this? So the answer is, unfortunately, a bit of math. What we're going to do is that we are going to subtract lowercase a from everything. So in other words, A minus A would be 0, right? B minus A would be 1, C minus A would be 2, and so on and so forth. And then we can use a bit of modular arithmetic to help everything wrap around. So what does that look like? Well, what I'm going to do is that I'm going to give you a function or help you write. So let me go ahead and help you write this function. So def encrypt car, or encrypt a letter and then the key is how we're, so that's what we need to take. Given a letter and a key, I want to encrypt it. Okay, so we can only really encrypt one letter at a time here. Okay, now this encryption function will work, but we might use a different This works for rotation ciphers, or when we have a specific key. Actually, it works for everything. Never mind. So, well, it works for a lot of things. But the idea here is that we have this letter, and what we want to do is figure out what it's going to be encrypted. And that means adding the key to it. Okay, so what we're going to do is that we're going to take the key's value, or to the key, or to the letter, and we are going to subtract A from it. And again, this gets it into the range of, so changes range from 97 to 122 to 0 through 25. Does that make sense? Okay. So this is the letter, the value of that letter. Okay. Now we can basically say that basically the encrypted val is equal to val plus the key. Okay. So in other words, if my original letter was, so if my key is 3 and my letter is T, okay, I'm going to switch T over to its numerical value. So this would be 25, 24, 23, 22, 21, 19, 18. So it would be 18, because starting from A, it would be 0, 1, 2, 3, 4, 5. So basically T is at index 18 in that alphabet. So when we subtract A from it, we're going to get 18. And then what we're going to do is that we're going to add 3 to it. UVW. Okay. So instead of 18, we'd be getting so 19, 20, 21, 22, 23. Sorry. I don't think I counted right. 25, 24, 23, 22, 21, 20, 19. Okay, so T should have been 19. Okay. Yeah. This is why I hate counting things manually. So T plus 3 would have given us 22. So 1, 2, 3, which is W. Okay. Now, what about though if my letter is Y? If I add 3 to Y, Y is 24, that gives us 25, 26, 27. There is no 27th letter of the alphabet in zero, when we go 0 to 25. Well, what we do want is we want B, right? We want to wrap around. So when we want to wrap around, we're going to use modulo arithmetic. How many letters in the alphabet are there? There's 26, which conveniently gives us the range of 0 to 25. Make sense? And now, what we do to get the letter back, now to give ourselves an actual letter, what we're going to do is we are going to take the encrypted value. We subtracted A initially. Now to get it back into the range of 97 to 122, we're going to add A back in. Does that make sense? Ord A. Okay. And now we need to just turn, and now that gives us a number, which we can then use CHR to turn into a letter. Make sense? So Okay. That changes the range back and converts it into a letter. And now finally, that's it. We just return it. Yes. Yes, encrypted val, my bad. Issues of talking and typing. Was that your question too? All right, so now let's test this by print encrypt a comma 3. I hope this works because, and so that gives me D, right? 3 after A is D. If I do Z, I should get C, right? And there we go. Z gives me A, B, C, which is 3 after that. Make sense? So I'm going to go ahead and share this code, hit the share button. And so now using what I've helped give you here, use this plain text. So what you're going to want to do is that you'll have this ciphertext over here. We have this ciphertext is equal to some empty string, and you want to convert this plain text. You want to encrypt this plain text into a ciphertext using a key of 13. Now remember, this encryption algorithm I wrote does one letter at a time. Why one letter at a time? Because there was a lot going on to just do a letter. So go ahead and finish that up so that it does so it gets the entire message. That should take about 3 minutes, 3 minutes at most. Unless you're lost, in which case I will help you with that afterwards. It's very hard for me to tell whether people are lost or not. So to share, so again, what you will need to do with getting the shared code is that you refresh the page and hit load history. But in case you need it, went ahead and posted it in the chat again. And I can post it on Discord as well. Assuming it starts up. Okay. Okay, and now I've turned on Do Not Disturb. That's good. All right, so what we should have here, I know it's been a very short period, but all we really need to do is, given the ciphertext, we go for letter in plain text. So for every letter in the plain text, we want to, we'll say encrypted letter is equal to encrypt the letter, and then we're encrypting by 13 as per the instructions. And then that just simply gets a letter, but so we're going to tack that on to the end of the ciphertext. Ciphertext plus equals encrypted letter. And now that should do it. Run. And what we'll see is that we get, when we check our test results, that we get when we encrypt the quick brown fox jumps over the lazy dog. We'll get this as our output. Which is Gerd Hivpo Bajaj. Yeah. It's unpronounceable. Yes. Caesar cipher with the shift of 13. So there's only 25 possible rotations. So first off, I'm going to share this and give you the chance to actually try to do this. The next one, and I'm also going to, you're going to want to use this encrypt algorithm, okay, over here as well. The problems Caesar cipher has is that there's only 25 possible rotations. If you're a clever spy, it won't take you long to write a program that will try possible combinations to unlock the plain text message. In fact, here's a new ciphertext unscramble. It's using a Caesar cipher, a rotation cipher, but it's not going to tell you the shift. Can you find the plain text message and figure out how the original message was shifted? Now, my hint here, by the way, is that to do a decryption algorithm, right? Encrypting, we don't really need to write a decrypt function too much, because encrypting by so encrypting something by 1, right? If I encrypted something with a by 1, it's the same as decrypting something with 25. Makes no sense. So if I encrypt A by 3, I can decrypt that. Instead, by subtracting 3, I can add 23 more. Does that make sense? So allow me to kind of show that in practice, because I'm getting some blank stares. So, right, if I encrypt a letter, so if I encrypt A and then 5, print, give me a second, print encrypt A 5, right? That's going to give me F. And then if I take F and encrypt that by 21, that's going to basically create a full circle. Does that make sense? So, right, 5 plus 21 is equal to 26. And encrypting the 26 gives you the same as 21. Sorry, encrypting 26 basically is the identity function when it comes to rotation ciphers. So that is my hint for you. And long story short, you don't even need that math. You can just basically try re-encrypting this. So go ahead and try to decrypt what the actual message is here. Now, here's the other thing. The computer won't be able to automatically tell you what the decrypted message is. You'll have to sift through the output of the computer to figure out what it is. Okay. It's not going to be able to say, oh, the answer was this. All right. I normally would give more time, but we only have like 20 minutes left in the lecture, and I want to get places. So I bet you've made pretty good progress on this. Now, just to simply emphasize the point, I did make a decrypt function over here. I copied over the encrypt function into here, and I created a decrypt function just to kind of show you this is what I mean. The only change that I named from encrypt to decrypt for rotation ciphers is that I changed everything that was named encrypt to decrypt. So the variable's name changed. And then instead of key over here, I have 26 minus the key, which is just simply moving it forward a bit. So what we do over here is that we are going to do a nice giant for loop. So for letter in, so to decrypt a message, right? Basically what we need to do is for letter in ciphertext, we could either encrypt it or decrypt it. It doesn't matter which one you use, okay? For letter in ciphertext, I'm going to use decrypt because that's technically just going to sound better. Real letter, or let's call it plain letter is equal to decrypt. And so the way decrypting works is that you need the letter and you need a key, which we haven't created yet. Don't worry about that. Okay. And then what we need to do is that we want to append that plain letter to the plain text. Plain letter. Just call plain. P. Plain text plus equals P. Okay. So what we want is that we want the plain text over here outside of this, right? Is equal to the empty string, and we'll just simply append something to it. And then when we're done with that key, we're going to print it. We're going to print it, and that's going to be printing plain text, of course, right? And then finally, but there's 25 different keys realistically. So we're going to try those 25 different keys. And we do that by creating a for loop. So all I did was just indent all that by selecting it and pressing tab. For key in range, because the key is a number, 1 through, and we want to go up to, but not include 26. So we'll print out the key and the plain text. And now, bad input on line 17. Uh-oh. For key in range, oh, right. Forgot the colon. And so if we look through all our output, we find only one thing that is not gibberish, which is Minnesota United Football Club. Right? That's what I meant by that you don't really have, the computer isn't really going to tell you what the answer is automatically. Because it doesn't know that this is gibberish, but this isn't, right? But we can print out all the things here and say, aha, I see actual things, which means this has an original shift of 17. So the point being here is that Caesar cipher looks secure, but it's not really secure. And it's very actually easy to check to see if you're using a Caesar cipher if your text is long enough by doing something called frequency analysis, which is that we look at how often each character occurs. Okay. And the idea here is that basically every single language has a frequency of its letters. So if your text is big enough, you should get basically a frequency analysis that looks like this, where one letter is occurring roughly 13% of the time, and another letter is occurring about 10% of the time, and another letter is occurring about 8% of the time. So if we see this distribution of letters, we know that it's in English. And it also means that basically that you're using some kind of one-to-one cipher. You're using either a rotation cipher or you're using something else. So we need something that has more than 26 possible keys. Yes. This? I will share this. Share. Okay. So the idea here is that if we, instead of, using, so what we did here is that we have this cipher and we just rotated it. But what if instead of rotating, we scrambled like this? Now that adds a lot more combinations, right? Instead of just having like one set like rotation key, we basically say, okay, all A's are N's and all P's become D's, but all M's become Y's, those kind of things. Right. So the idea here is that there's a lot more possible. So if we do a rotation cipher, there are 26 factorial possible permutations. Sorry, keys that we can use. Rather than being a number, we can say, okay, the key. So what do we want to encrypt for A? We have 25. What do we want A to encrypt to? We have 26 possible letters for that encrypt to, including A. We could have a letter encrypted to itself. Let's say K. And then we have 25 possible letters for B to encrypt to. And so on and so forth, right? Basically see that I'm just kind of saying, okay, this letter translates to this letter, and so long as I don't repeat anything, it's all going to work out, right? So how do we do this? So for our Caesar, we did modular arithmetic. Instead here, what we're going to do is that we are going to translate directly. So here the alphabet was this. And our key is this. So we want in our output, we want all A's to be M's, all O's to be S's, all F's to be B's. So here, instead of, we would have a O, we would have an S, B. But we don't have to limit ourselves just to letters. Anything that's a space, we're going to translate to as a Q. So it would be, so the first three letters of our output would be SBQ. And anywhere we saw in E, instead we'd replace that with a space, because why not? So how do we encrypt this, right? Well, we've got our ciphertext. Well, here we would make use of the index operation. Basically, everything in the alphabet, basically what we want to do is that we want to say, okay, I've got an O, that's the letter I want to translate. How do I turn it into how do I turn my O into an S? Well, O's at this index, which is the same index as this one. So I just have to find the, so I find what the indexes of this letter is. And then I translate it, and then I basically get the letter at this index in the key. Make sense? That's one way to do it. Another way to do that is to, which I find a bit easier and more straightforward, is a dictionary. Is equal to this, or letter for plain, comma, encrypted in zip, which allows us to loop through two things at once. I will actually call this for A and K, for A in alphabet and K in key. That makes a bit more sense. Then set up so that cipher of A equals K. Does that make sense? Basically, if I pass, so what this does is that it sends up a mapping between the alphabet and the key. So if I say, hey, if I ask the cipher, hey, what does T translate to? It should give me H back. And in fact, if I ask it for that, print cipher of T, it will in fact tell me H, because it goes through each of these pairs. It goes basically AM, BW, CG, DP, right? It goes through both, it goes through them sequentially. Zip is very useful. Okay, now that I have that, what do I need to do? Well, now I loop through the plain text and append everything. I'll do this one, and then we'll move on to the next one. Right? So for letter in plain text, annoying, ciphertext plus equals cipher of letter. And if we run this, we pass it, we get the appropriate encrypted text. So what about decrypting it, which will be our last exercise here. So now that you've tried to encrypt it, I'll go ahead and share this code. Now that you've been able to encrypt it, now do the opposite over here, which is decrypt it. And it works the exact same way, just in reverse, which is that what was the value in the dictionary instead needs to be the key, and what was the key in the dictionary needs to be the value, right? So in other words, to decrypt it, if I give the dictionary an A, I want to get an M back. If I give it a Q, I should get a space back. If I get a space, I should get an E back, right? Whereas when we were encrypting it, we were working from the alphabet going to the key. To decrypt, in this case, we're going from the key to the alphabet. So go ahead and try that with in the last couple minutes, and then I will fill it out for us. Okay, so what I'm going to do is I'm going to make a dictionary called which I will just call decrypt. And I'll do the same zip operation for alphabet. It's not the only way to do this, by the way, as I mentioned. For alphabet, so for A, K in zip alphabet key, in this case, what I'm going to do is that instead of doing AK, I'm going to do KA. Decrypt K is equal to A, so that we can go in the other direction. And now plain text is equal to empty string for letter in ciphertext. Plain text dot append, not append. Plain text plus equals decrypt letter. That's it. And the sun was shining on the sea, shining with all his might. That is our decrypted message. Share code. Okay. Now, there are more algorithms that exist for encryption. A lot of encryption algorithms are based off of something called, let's see. So actually I can check right here where if I go to Wikipedia, and I click on the lock button, I can actually see connection secure, more information. And it's going to tell me that the connection was encrypted using AES 256, which is the encryption algorithm right over there. So if you want to learn more about those algorithms, you can look up, I'd start by looking at RSA. The RSA crypto system, which is named after the authors. It's one of the oldest public key encryption systems. It's relatively slow, but it is, a good place to kind of learn about those things. The issue is that in today's world, encryption, computer security and the usability of networks have divergent models, divergent and contradictory models. The idea here between networks is that you've got to trust somebody to connect to the network. You've got to trust that the router is who he says he is, the site you're connecting to is the site you think it is. Where security says you can't trust anybody. Nobody. And it's really hard to kind of, create an approximate area where that thing is. You can't, the only way I can guarantee a computer is secure is if I've turned it off, unplugged it, encased it in cement, and buried it at the bottom of the ocean. And even then, I wouldn't put good money on it. Because again, computers are tools used by humans. And so we want the information that's produced by humans. So humans are the weak point in this system. So anyway, there is no such good thing as perfect security. It's just simply making things as inconvenient as possible for bad actors. All right. So I think we'll do another exercise on Thursday, and then I will work on giving us more time on Tuesday and Wednesday. Sorry, Tuesday and Thursday next week. We'll work on reviewing for the final exam. All right. I will see you all on Thursday.